Dear students, in today's video, we are going to discuss torque acting on an electric dipole when it is placed in uniform electric field. It is one of the important long questions asked during the exams. By watching this video, you will come to know what is uniform electric field and how the dipole behaves when it is placed in uniform electric field. Let us discuss what is dipole. Dipole consists of equal and opposite charges separated by a distance 2a. In this figure, plus q represented in black is one of the charge and minus q is the second charge. Both charges has magnitude QQ, but they bear different sign, so they are opposite charges. They are separated by a distance 2a. O represents the center of the dipole, which divides 2a into equal parts. So, plus q charge is placed at point A here and minus q charge is placed at point B. We know that dipole moment can be calculated by the product of the magnitude of the charge and the separation between the charges which forms the dipole. The force can be calculated by using the expression. It says that force is product of the test charge multiplied with the electric field strength. So, here the charge is plus q, which is placed in uniform electric field E. So the charge plus q will experience a force which is QE. For the another charge, that is minus q, force will be minus q into E. Both the forces are equal in magnitude, but the force acting on plus q charge is along the direction of E. It is upward, while the force acting on minus q charge is in the downward direction, that is opposite to E. Now, electric field is uniform, means the electric field lines are parallel. They are equally spaced. The electric field lines are parallel and equally spaced. So, the net force acting on the dipole is given as the sum of the individual forces, that is QE minus QE, and it comes out to be equal to 0. Now, the forces acting on the dipole are equal, unlike as they are in opposite direction. These forces forms a couple which rotates the dipole in anti-clockwise direction. The dipole rotates in anti-clockwise direction. We draw the line BC, which is perpendicular to the electric field. This BC is equal to arm of the couple. By knowing the expression for the torque, that torque is the product of the force into the arm of the couple. Force is the F and arm of the couple is BC. This BC can be calculated by using this relation, that is PBP HHB SCT sin, cos and tan trigonometric relation. When you apply this relation, then the angle theta is here, that is the orientation angle of the dipole. The dipole is placed in the electric field at an angle theta. So if this angle is theta, as the electric field lines are parallel, this angle is also going to be theta. It forms a right angle triangle with this angle as theta, this separation as 2a, and this is the BC which we want to calculate. By using this trigonometric relations, BC is the ratio of perpendicular to the hypotenuse and the line which is in front of the angle theta is the perpendicular. So it is BC divided by the hypotenuse, that is 2a, is equal to sine of theta. So BC comes out to be 2a sine theta. So it will be QE multiplied with 2a sine theta. The terms can be rearranged. You can write Q into 2a, because you know that this Q into 2a can be written as P, and this P is the magnitude of the dipole moment. Then we have put Q into 2 as a P into E into PE and sine theta, and we know that the cross product of the vectors is written as A magnitude into B magnitude into sine of theta. If you implement this thing over there, your A vector can be replaced as P vector, that is the dipole moment vector, and E vector is your B vector. So by using this relation, you can write torque as a P cross E. So one thing is concluded here, that the torque is a vector quantity and this torque is perpendicular to both dipole moment vector and that of the electric field vector. So the torque lies perpendicular to the plane in which your dipole moment and electric field vector are placed. Now we will discuss special cases. The special cases originate by changing the orientation of dipole inside the electric field. In first case, we place the dipole along E vector. You know that the electric field starts from the positive charge and ends at the negative charge. So, you have placed a dipole which is placed parallel to the electric field lines. Plus Q is placed toward the minus of the electric field and minus Q is placed along the positive of the electric field, and the direction of the dipole moment is from minus Q to plus Q charge. So dipole moment has upward direction. This is same as that of the electric field. So when theta is equal to 0, torque is equal to PE sine theta. When you substitute theta is equal to 0 degree, as both the dipole and the electric field are placed parallel to each other, the angle is 0, then the total torque tau comes out to be 0, and this stage is called the stable equilibrium state. In second case, we will take the angle same. We will keep theta is equal to 0, but we will change, or you can say we will reverse the orientation of the dipole. The minus Q charge will be taken upward and the plus Q charge will be taken downward. For the second case, when we do so, we plot the figure again. Plus Q charge is at the bottom, minus Q charge is at the upper side. Then this dipole is held opposite to the direction of electric field. Such a dipole will be unstable equilibrium dipole because dipole moment has downward direction while the electric field has upward direction. Dipole moment is acting downward while the electric field is acting upward, due to which the dipole is in unstable equilibrium. In third case, what we do, we want to have your torque to be maximum. If you want your torque to be maximum, you know that the angle involved is theta and sine theta is maximum at 90 degree and this value is equal to 1. You place your dipole perpendicular to the electric field, which makes your sine equal to 90 degree, and the maximum value of torque is equal to the product of the magnitudes of the dipole moment and electric field. Now, the next is the calculations for the units of torque. We have derived this relation that torque is the cross product of P into E. P is the dipole moment, that is Q into 2A. We can club this Q and E, and Q into E combination will give us the force multiplied with 2A. And you know that SI units for the force are Newton and SI unit for distance or displacement are the meter. So Newton meter are the units of torque. Then the dimensional formula can be calculated. Torque is the product of force into displacement. Displacement will give me L only, and the force is mass into acceleration, right? And this is mass into acceleration. This all things you have done in your +1 class, that is velocity upon time, and this is mass into velocity is again displacement upon time. So it will be m power 1 from here, L power 1 from the displacement, and t raised to power -2 from the time. So it will be ml m1 l1 t -2. So we combine this l1 with this l1, it will give me l2. So it is m1 l2 and t -2. These are the dimensions of torque. I hope you find the content useful. Kindly like, share and subscribe my channel. Thank you.